Morning. My name's Tim Mann. I'm one of the product specialists that looks after thermal analysis for a company called PerkinElmer. Little bit of background for myself. I'm a material scientist, so I spent X years at university playing with all of these sorts of materials that the Formula One guys now use. I'd like to talk a little bit today about how we help Renault in this case, but also other Formula One teams help solve their problems with regards to composites, polymers and other problems that they have. I'm a bit of a Formula One nut, so I'm afraid if I get a little bit excited as I go along, then I'm not going to apologise too much, but I've been watching the sport for quite a few years. Those of you who haven't seen thermal analysis or know the technique, just a little bit of a background as to what it is and what it does. So basically these are analyzers that are used for looking at changes in materials properties. So whether that be melting, whether it be decomposition, the material itself is actually changing in its structure as you heat it up or cool it down or do something to it. So there's a little bit of a list here about some of the things that we do and why we do it, but I'm not going to labour the point too much with this, but I'll be showing you some of the reasons why the Formula One guys use these bits of kit to help them with their problems. So, if you've never looked at a Formula One car, then they're about 80%, probably a little bit more now, carbon fibre composite. So obviously the engine itself, you'd look at that and go, well, there's no carbon in there. Actually, there now is. The gearboxes especially are now carbon fibre. The reason why that's done is it's obviously a weight saving, but also it can be repaired. So if you get a hole in the side of a gearbox and it's metallic, you have to throw it away. The rules now are that I think you're allowed five gearboxes or 5 parts of the gearbox throughout the year. So if you can repair it, that doesn't qualify as the gearbox being replaced. So most F1 teams now have gone to carbon fibre gearboxes. So as you can imagine, the stresses and strains and temperatures that these things experience means that you've got to really know what's going on with it. So how do we help them? Well, some of the stuff I'll show you today is based around the tyres, hence the term burning rubber. We can obviously look at the engine with the gearbox. We can look at the lubricants and the fuels themselves, so the actual oils and things like this that go into the gearbox. Obviously the bodywork. Now you look at a bodywork on an F1 car and think, oh well, that's obviously really structural. Most of them are only 1 or 2 millimeters thick. It's advertising. It really is advertising space. They're there for aerodynamics as well, but a lot of it is because it's painted and you can slap nice people's sponsors' names on it. Most of it isn't actually structural, but it has to be secure if nothing else. So why do we use composites these days rather than metals? Well, there's a big long list of things here, but the important thing really is this figure here. Pointers, by the way, never work on these television screens. This figure here, 785, so this is specific strength. So this is how strong it is compared to how big it is compared to how much it weighs. So if you compare that to titanium, which is one of those materials that you think, well, why wouldn't you make it out of that? Unbelievably light and strong. But carbon fibre epoxy composites are so much stronger, and that's really useful for situations like this. Now normally I would have a video clip, but from today's point of view I can't. This was Fernando Alonso, who crashed his car at 190 miles an hour. He went over the back of Esteban Gutierrez's rear wheel and basically spun it in midair, pulled 86G at one point. The car's a little shorter than it should be. He walked away with 2 broken ribs and a slight punctured lung. 3 weeks later, he was back in the car and racing again. Unbelievable. If that had been a metal car, or go back years and years ago, sadly, the chances are he wouldn't have walked away from the crash. So this is the reason why carbon fibre composite is now so important for the Formula One teams and why we help them. If you've never seen how one of these things is made, it's quite a hands-on sort of thing really. You take a piece of what they call pre-preg, which is carbon fibre with the epoxy resin in it. You cut it to a nice shape. You have lots of layers. You build it up by hand. Then you put it into a mould, which is the one on the left. Suck all the air out of it. Shove it in a big oven. Heat it up. And then it all solidifies, cures together, and then you can put it on the car. So the other thing is, though, is a lot of people don't know, is that most of the car is glued together. Most of these things are not made in one piece. They stick them together. So you can see here, this is a front wishbone. So it's all nicely carbon fibre. And then on the far left-hand side, or on the right-hand corner, you'll see you've got titanium end parts. So these have to be physically glued in. So you need to get not only the carbon fibre right, but the glue right. Because obviously if the glue's wrong, it'll fall to pieces, which again is probably not a good thing at 180, 200 miles an hour. I think 215 I think they were doing this weekend in Mexico. It's quite quick. So this is where I come in, and the support that we give. So what this is, squiggly line, is basically what they do. The material, to make sure that it doesn't go off so they can use it, means that it's stored in a freezer. So that means they actually have to know and make sure that the transition down at the far left-hand side of the screen here is in the right place. If that's too low in temperature, too high in temperature, or too small, then this material's changed. So you don't then make your car out of it, because it will fail, potentially. When they actually cure it, so like if you have your Araldite glue at home, so the two-pot glue, this is the same principle. So you're mixing the resin and a hardener together. Just mix it all together, and when it basically reacts, it gives out energy. So this peak on the right-hand side here is basically the resin reacting. So this is the actual energy that's given out. That has to be within a specific range, not only of temperature but of energy itself. If it's too high, then you'll get the wrong properties. If it's too low in energy, again the wrong properties, which means things flap off, fall to bits, which again is not good at 200 odd miles an hour. So they use it as a quality control test. So it's a very simple test, which is basically here. We have these two. This is called a glass transition, and this is basically the temperature moving to a higher temperature if the material is cured properly. So if this blue line is in the right temperature range, you can use it. If it's not, you don't put it on the car. So it's a fairly simple test, and that is just based upon, is the material cured enough? Has you given it enough time? Or has it reacted sufficiently to actually all hold together? So, interesting thing for me is this is actually a carbon-carbon disc brake. So modern Formula 1 cars and anything else now uses carbon-carbon, but it's something I'll show a little bit later. But we use another technique, which is a mechanical test. So far I've been talking about energy flow. This one is basically, if you imagine getting hold of a piece of composite and bending it. So we're physically bending it and then heat it up, and when we can then make sure that it bends the correct amount in the first place. As you warm it up, does it soften? Does it bend too much or not enough? So the technique we use is called dynamic mechanical analysis, and this is what we're looking at here. So I'm a material scientist. I want to know at what point my piece of car starts to go bendy. So we heat it up, so you see we're going from 0 degrees roughly up to 350. The blue line is basically the stiffness, if you like, of the material. So we're looking at it being quite stiff. You can't physically bend these things. We heat it up, and eventually it goes down, drops down in its stiffness quite dramatically in this case. Now that's useful to know for two things. One, what temperature does it do it? But also, how much does it change? If you think about this from where these materials get used, you've got an engine at the back of the car with a big exhaust on it that's running at about 1,000 degrees C, and you've got something carbon-based near it. You need to know whether it's going to go floppy and at what temperature, because it's going to get warm. So this is the test which is routinely used. And again, it's done from a quality control test, if nothing else, but mostly performance. And if you've got one that shows a bit weird, then you know you've got a problem. So what happens with this material is, a bit like the last one, you heat it up, it starts to go floppy. So the blue line is going down, yeah? And then suddenly it starts getting stiff again. And that's because this bit of carbon wasn't cured properly. So it started to go floppy, and then it started to react again, so it starts getting stiff. So then, again, for them is a problem. We know it's not being cured enough. It's likely to cause a failure on the car, so you go away and do something else with it. Normally put it back in an oven again and heat it up. Or, years and years ago, do you remember the McLaren SLR? It's a really, really expensive supercar. I was doing some sort of work with the guys down there with this, and it turns out that they cured it wrong. So I isolated this problem for them and said, right, you need to go and post-cure it. They said, no, we can't do that. So they picked the whole subframe up, which was worth about £25,000, chucked it in a skip out the back. So my claim to fame is I have binned McLaren SLR. Well, not quite. Wish I'd been driving it and binned it, but anyway, that's a different conversation. So this is really, really important for these guys. It's the same with aerospace and everybody else that works with composites. Knowing your material is cured correctly. Why is that a problem if you don't get it right? Well, this is a Toro Rosso from about 8 years ago. Was doing 140 miles an hour down the straight, and it's basically its front supports for the wheels snapped. Both of them at the same time. So as you can see here, one wheel on the left, one wheel on the right. Needless to say, the car doesn't steer very well without them. And he just went in a straight line into the barriers. It was slowing up quite a lot by that point, but again, you don't want this to happen. This was under virtually no load at all. This was just literally in a straight line on the straight. So getting your cure wrong is a really, really bad thing. Really bad. So what we do is we plug a little bit into the machine, bends it, and away we go. But what we can also do is use this for looking to see the change in stiffness. So this is a material that's reacting now rather than heating up. So the black line going upwards is basically the change in how this material changes in its stiffness. So this, if we left it long enough, at 800 minutes we got bored and decided, you know, that's enough. 10 hours is sufficient time to sit and watch this. So, but if we'd left it a long enough time, it would have come to a plateau. So then you can see the difference in the step from a performance point of view. Is it going to be stiff enough? So again, a test that's routinely used to make sure nothing falls off on the car. The other thing that we need to think about, though, is this. If you heat a material up, does it expand? Does it contract? How does it change? So again, same thing, back of a car, got an engine that's getting up to a couple of, maybe 1,000 degrees C. You've got hot exhaust gases coming out from the exhaust, and you've got carbon fibre sort of vaguely near to it. If this thing starts to expand, what's that going to do to the component that it's attached to or a part of? Is it going to crack? Is it going to start pushing onto something else that then fails? It's hard to know. So one of the tests that we do with the guys is looking literally at what's called the expansion coefficient. Does this material increase in its size with increasing temperature? So if you take something like that, so this is a piece of carbon fibre, and what we've done is we've put it flat on one edge and then we tipped it onto this other edge just to see if it changes in how much it expands in different, depending on whether you're looking at, say, the through plane thickness or the width. And you can see from the two different lines, the red line compared to the black line, there's a very, very big difference in how this material expands. So you have to be really careful as to where you put this on the car, because it may well be that if it heats up, it goes sideways, pushes into into a set of wiring or onto a pipe, or it then actually expands and actually touches the exhaust itself and then sets on fire. So very, 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 again, important information. Something really basic. Just does something get bigger or get smaller when you heat it up? The other one, though, is this. We can also do exactly the same test by taking this and bunging it into immersion. So if you imagine taking your bit of carbon fibre composite and pushing it into well, in this case, my thing of water, but equally it could be a fuel. This could be a component that's actually in part of the fuel tank, or it could be with the gearbox where the oil is involved. What does that actually change how this thing behaves, just purely because of the fact that it's in contact with a solvent, whether it be water or oil or fuel or whatever? And what you can see here is a set of different rubbers in different solvent. So you've got natural rubber in alcohol, does absolutely nothing. In kerosene, it actually expands by about getting on for 10%, which is quite a lot. If we put it into xylene, these then becomes different rubbers, so a silicon rubber, a natural rubber, an NBR, whatever. Again, in xylene, there's quite big differences, but you're looking at nearly 30% that this bit of rubber actually swells, just purely by putting it in contact with a solvent. Again, all absolutely vital bit of information with making hoses or seals or anything in the engine. So, really, really powerful bit of information. And all of these things just build up the picture, because for them, all they want is the car to do the entire race distance, as fast as they can. So anything that causes them a problem, they want to get rid of. And then we talk about tyres. Those of you who've been if you watch the Formula One will probably be as confused as I am these days with tyres. We go from the super hard, which apparently Pirelli made because they felt like they should, but will never actually be used because it's so hard the car can't actually almost get round the track. There's no grip. And then we go through to the ultra mega super whooper softs, the pink ones, which last about 5 laps if you're lucky. So this tyres are just these things that we all shove on our car. We don't really think about it. It's just a tyre, isn't it? It's a bit of rubber. They are unbelievably complicated, and it's a black art. The guys at Pirelli or Goodyear or whoever who make these tyres will never tell you what's in them. And the reason is because if you take a list, and please don't read this because it's highly tedious, but you can see there are hundreds of components that are in this tyre just to make it grip the road. And it changes, even on your road tyre, between one manufacturer that's got really grippy tyres compared to one that's designed to use in the winter, compared to one that's designed better in the wet. They can change how these tyres behave purely by changing the components within it. So what we do is we help them to work out what's in it. So this is basically, it's called a TGA, so it's a balance in an oven, if you want to put it simply. So what we're looking at here is about 8% of something, about 45% of something else, about 8% of something, and about 25% of something else. So this is individual components decomposing at different temperatures. But this allows us to get a feel for why the tyres do what they do. So if you take a look at different types of tyre, you can see there are some quite big differences between the green one, the blue one, the red one, and everything else. But realistically, what we end up looking at, because my pointer won't work, is this endpoint here is the amount of, if you like, filler. So stuff that will not burn, will not decompose. So things like titanium dioxide or silica or whatever in the actual tyre itself. So you can see there's some quite big differences between one that's nearly 40% and one that's maybe a couple of percent. And the step before it, this says 35 minutes on here, but this that step there, the blue and the red, this one here, this is carbon black. So this is the amount of carbon that's in it. And you can change how sticky a tyre is by changing the amount of carbon black that's in there. So these are the sorts of tests that we play with the F1 guys in order for them to understand what goes on with their tyres. But the question then is, okay, there's how much of it is there, but what is it? You said it's 8% of that and 35% of this and 64% of that, but you don't tell me what that is, and they need to know, and we all, so it's useful for them to do. So what we do is we stick a nose on the end of our TGA. So this is if you like a stylized TGA. So balance in an oven. The green bit is our bit of whatever it is, and we basically suck the gas that's coming off and shove it into a nose. Now that nose can be an infrared spectrometer. It can be a gas chromatogram with a mass spec attached to the end. It can be a mass spec itself. It could be pretty much anything. But what it's doing is it's taking the gas and it's telling us what it is. So, picture of one, which we'll carry on with. But this is a different tyre. This is actually a road tyre. So rather than a Formula One, but the same things apply. There's a big weight loss, and what we're going to do is we're actually going to collect the sample there. We're going to go, I'll wonder what that is, that bit of gas that's coming out at that point. Will this tell me what the tyre is made of, or what's letting go on the tyre? So we then take the gas, suck it into a gas chromatogram. The GC, if you remember your old chromatography at school, where you take your bit of ink on a blotting paper, run it up, and it separates out into the individual colours. Same thing, but doing with columns and purge gases and stuff. But basically we're separating the individual components out. And what we can then do is use some quite trendy software and what's called a Nist searchable database, and it then tells us what these components are. So when this tyre lets go, it's giving isoprene, which is a type of rubber. We've got toluene, which is part of a solvent that's in there maybe. We're getting styrene. So we all heard of polystyrene, as this is the individual component from it. And then, funnily enough, limonene. Well, that's the smell of lemon. But in this case, this isn't actually from lemon. They don't make the tyres smell of lemon. This is the isoprene, actually, basically, because it's being heated up, actually basically reacting with itself and turning into another compound. But this is giving us a feel for what comes out, what comes off with it. And we can do this with any material, but in this case we're doing it with rubbers. And the other thing we look at with these with the Formula 1 teams is brakes. I was showing you the brakes before. These are quite complicated carbon-carbon discs. So you've literally got layers of carbon which are bonded together with different chemicals and everything else. And I don't know if you ever watched one of the races, but you get people complaining about getting brake fade, or the brakes basically don't work, or suddenly they wear the brakes out and they burn through them completely. And so that's just because of the wear characteristics. But what we can do by looking at different compounds and different temperatures is actually work out how the brakes are failing and why they are. And can we change the chemistry of it to stop it from happening quite so easy, but still retaining the adhesion of the pads onto the discs? And so this is what we've done here. So again, TGA. So you can see the red line coming down. So we've got different weight losses. These are at different temperatures. But what we've decided to do is take a look at a couple of different temperatures on this one. So about 570 degrees, which on a normal brake is about when it's getting really hot, when you've really stamped on it, the car's trying to stop. This is about the temperature you'll get to. So what comes off? We've got some CO2, fair enough. It's a carbon brake, bit of oxygen knocking around, it's going to give off some CO2. But we're getting benzene, we're getting toluene, xylene. Oh, by the way, so don't smell your brakes. I know you're not likely to, but some nasty stuff comes off. We've got some methylphenol, we've got some silane, some benzonitrile. There's some quite nasty compounds coming off this. But this is telling them how the brake is breaking down. Which part of it? Is it the binders? Are they using the correct stuff to stick it together? So at this temperature, they know which part of the brake disc is starting to go. So they can change that potentially. So this is just showing benzene being put, how we actually pull it up. So this is how we help them. It's been a real whistle-stop tour, so I've really have sort of hammered through it a little bit. But these bits of kit are used by the teams just purely so that they can take a car, put it on the track, make it go around the track without breaking down, and hopefully if they do crash, their drivers can walk away. So anyway, thank you very much for your attention. I hope that's been useful, and enjoy the rest of your day. Thank you.